Now we're going to try to apply the subnetting concepts to a real-life design that'll help you understand how it's actually applied. And when dealing with subnetting, and looking at the example on the board, I have a number of LANs, and I'm going to try to apply a subnetting concept to it. So in the case here on LAN A, or local area network A, it seems that I only have 6 hosts attached to the switches. But the one thing you have to remember is you always have to include the router as one of those points of interest. So technically there will be 7 hosts that are required for addresses on LAN A. For LAN B, what will be required is approximately the same amount. You'll know that there's 6, there's 8 physical computers or hosts that need addresses, including the router, which would be 9 valid hosts on that LAN. When looking at LAN D, you'll notice how there's a little bit more hosts. There's 9 hosts, including the interface on the router. Therefore, what will be required is 10 hosts. And for E, we would require the same amount of 10 hosts. One thing you can't forget about is LAN C, because technically, even though that's between the routers, it's still a LAN of 2 individual IP addresses. Therefore, the requirement is 2 hosts. Now, when dealing with addressing from a real-life perspective, a registry will normally assign IP addresses or networks to you as a company. And in this case, let's just say they assign the address 192.168.100.0 with a /24 mask. Now you might be saying to yourself, that really isn't enough to give me what I need, because that prefix with that mask would only give me one network with up to 256 hosts. The network number being the 192.168.100 portion. The .0 would give me 8 bits. 2 to the 8th power would give me 256 combinations. And as we've learned in a prior lesson, there would only be 254 valid addresses from that. So the point of this is to show you that subnetting is the responsibility of the person receiving the address from the registry. So in doing subnetting, we have to specify what the requirements are. And in this case, the requirements are really 5 networks or 5 LANs. And when dealing with the host portion, you'll always go to the highest number of host requirement, which would be LANs D and E, which would be 10 hosts, because 10 hosts is the highest requirement. So we really don't need one network with 256 hosts. We need 5 networks with 10 hosts apiece. So in this example, we're going to try to figure out what mask would work instead of being given the mask data as we have in previous lessons. So here's your 192.168.100.0 network with a /24, which happens to be the default applied. So in trying to figure out what mask would be the best, let's start off with, say, a /30 as an example here. With a /30, or 30 bits of ones from left to right continuously in the mask, we'd see that that probably wouldn't be enough, because the zeros portion is what the router would see the increments in. And with this particular mask, you would only be moving in sets of 4, because you only have 2 zeros. Therefore, the router would see a change every 4 numbers, and 4 hosts would definitely not be enough, especially when you include the fact that 2 of those hosts would not be usable. So let's try a /29. In looking at a /29, you'll have 2 to the 3rd power host bits, or 2 to the 3rd power zeros there, which would still give you 8. Take away 2, you'd only have 6 valid hosts there, so that's not enough to fulfill the requirement of 10. So then we move to a /28. Now, a /28 would give me the minimum requirement, because the hosts portion would be 2 to the 4th power, which would be 16 hosts, minus 2 not being usable. You'd have 14 usable hosts, which would take care of my highest requirement of hosts. And even if you look at it from the network perspective, you'd have 4 ones there, and 2 to the 4th power ones would also give me 16 networks. Of our requirement of 5 is what we needed. So when trying to use this type of scheme, which I believe works as a minimum, let's go ahead and list all 16 networks, beginning with 0 and ending with the 240 network. Even though we see all 16 networks here, of which there are 16 addresses available in each network, only 14 usable, we're only going to require 5 of them to apply to the example. Let's go ahead and lay out those 5 networks on where we would place them. So here, looking at LAN A, Here's where I would put the .0 network. And when applying the host, you'll notice that .1 would be given to the router, which would be the first available address. .2 would go to another host that's sitting off the LAN, off one of the switches. .3 to another one. .4, .5, .6, and .7. Now, we only require 7 addresses, but we have a few more for growth. In fact, we have up to .14 on this LAN to grow hosts. So now we're looking at applying the next network, and the next network we apply, since we're in sets of 16, would be the .16 network. And the .16 network would go to the other wire, beginning with .17 that we apply to the router, and so forth with all the users. The last usable host being .30, 31 being the broadcast, and 32 would be available to apply to a different wire, in this case applying it to LAN C, which only uses 2 addresses. I plan on covering this in a further lesson on how this is wasted space and can be used a little bit more efficiently using something we call variable length subnet masking, also known as subnetting the subnet. In assigning the rest of the addresses, you'll notice on LAN D, the next network available would be .48 with its available address space, and finally .64, which would be our 5th network that we could use. And really another correct way of looking at how these subnets are allocated would be pretty much as if we allocated them to each interface off of each router, which is why it is sometimes referred to as a wire address, with many hosts sitting off each wire.